an eigenvalue problem with indefinite weights. Let omega be a bounded smooth domain, connected domain in Rn with smooth boundary. We consider the following eigenvalue problem with Neumann or Dirichlet condition, where A, here there is a weight A, is a non-trivial sign-changing function. The Neumann problem is of current interest as it is a linearization of a nonlinear equation arising in population genetics. The scalar equation has been widely studied, beginning with the work of Bocher, Hilbert, and Richardson. And the first work for the Dirichlet boundary value problems in 2 dimensions goes back to Holmgren at the beginning of the last century, who considered the equation in bounded domain in 2 dimensions, proving the existence, if A changes sign, the existence of 2 sequences. One sequence of positive eigenvalues with associated eigenfunctions, and a sequence of negative eigenvalues with associated eigenfunctions. For the general result, we have to wait a more recent result that is due for the first in my knowledge to the work of Manes and Micheletti, that they proved the existence of these 2 sequences for a more general operators, and gave a variational characterization of this eigenvalue. Their aim was to generalize the assumptions for the Ambrosetti-Prodi problem that I think everyone here knows. They consider a convex nonlinearity which crosses the first eigenvalue of the Laplacian, and Ambrosetti and Prodi gave a global description of the solution structure of the associated Dirichlet problems. The linearization of the nonlinear mapping needs to be controlled in every point of the domain space, which leads to consider eigenvalue problems with some weight which changes sign. After the work of Manes and Micheletti, there were a lot of amplifications and new formulation from different authors and from different point of view. For instance, the work of Berger and Podolak, we consider the problem in Sobolev space, the famous works of Church and Timorian, the global cusp of Roof, and also the generalization of Carlos and Boyan for non-self-adjoint operators, and also a converse of the problem of the Ambrosetti problems. Essentially, these works treats the Dirichlet problem. Here, I want to concentrate the attention to the Neumann problem, which, in my opinion, presents some peculiarity that I find interesting. So let's go back to the eigenvalues problem with Neumann condition. If A is a sign-changing function, we can consider the bilinear form S. The bilinear form S defined as in the second line, and we can consider the two sets, B plus, which is the set in H1. H1 is the usually Hilbert space of L2 function with derivative in L2, for which the quadratic form is equal to 1, and B minus is the set of U in which the quadratic form is equal to minus 1. This, if A change sign, these two sets are not empty. So we can consider the first eigenvalues as with this variational characterization. There is one non-negative eigenvalue, which is lambda 1 plus, which is the infimum taken on B plus of the norm of the L2 norm of the gradient, and lambda 1 minus is minus the infimum taken on the B minus. These two first again, these two infimum are attained and give the two in general two different eigenvalues. These eigenvalues are simple with eigenfunctions which do not change sign. More precisely, if the integral of A is negative, then the first non-positive eigenvalue is equal to 0, and the first positive eigenvalue is actually strictly positive. If the integral of A is greater than 0, then the first negative principal eigenvalue is strictly negative, and the non-negative, the positive eigenvalue is equal to 0. Okay, it's trivial that for the Neumann problem, the eigenvalue lambda is equal to 0 is always an eigenvalue. And in the degenerate case, when the integral of A is equal to 0, the two principal eigenvalues collapse, and there is only one eigenvalue, which is the trivial one. For higher eigenvalue, we can give this variational characterization of the eigenvalue, which is the usual characterization of the eigenvalues. Now I want to concentrate my attention only to the first eigenvalues, since sorry, sometimes okay. And what about the eigenfunctions? If we have two different eigenvalues, lambda and mu, and phi lambda and phi mu are two associated eigenvectors, then these eigenvectors are almost orthogonal in the sense that the gradients are orthogonal in L2, and the bilinear form is equal to 0. Moreover, the eigenfunctions, as I told before, corresponding to the first eigenvalues, have constant sign. And these are the only eigenfunctions that have constant sign, in the sense that the eigenvalues lambda, which are not the first eigenvalues, do not possess a positive eigenfunctions. These, the first two properties are very elementary to prove. The third is a little bit more difficult, but there is a beautiful proof in the work of Brown and Lin. Now, this was all these results are very well known. Now I want to consider a perturbation of the linear equation and consider the first trivial perturbation of the linear equation. So we consider the following superlinear problems. P plus is the case when I had the power up to the linear equation, and we consider the existence or not existence of positive solution for the Neumann problem in both cases. In the case where we had up, this power, or in the case where there is minus up. P minus, I call P minus the coercive problem, and this will be more clear later, and P plus the non-coercive problem. For the coercive problem, we have that if A is a sign changes solution, a continuous sign changes solution, and this this assumption can be a little relaxed, but now I want to discuss classical solutions. So I take a continuous function, and P is greater than 1, then the coercive problem has a positive solution if and only if lambda is outside the interval, the principal interval, that is the interval between the two principal eigenvalues. For the non-coercive problem, there is a sort of complementarity. That is, if we have the same assumption on A, that is A is a sign changes function, and P we need a restriction on P. P is subcritical. Then the equation P plus, the non-coercive problem, has a positive solution if and only if lambda is between the two principal eigenvalues. Just a remark on the degenerate case. The complementarity is most striking in the degenerate case when the integral of A is equal to 0. In fact, in this case, we have only the trivial eigenvalue, and hence the coercive problem has a positive solution for every lambda different from 0, and the non-coercive problem has no positive solution for every lambda. For the proof of non-existence of positive solutions, in the case lambda equal to 0 is trivial. Just integrate the equation, the integral of the Laplacian is equal to 0, and then you have that there is no non-trivial solution of the equation. For the existence in the coercive case, I will discuss it more later on. Okay, only a picture of the situation. Above we have the equation for the coercive case. Okay, on the left we have the classical case when A is a weight which is definite. For instance, take A equal to 1. Then we have that for lambda greater than 0, we have the principal eigenvalue is lambda equal to 0, and for lambda greater than 0 we have at least a positive solution, and the non-existence for lambda less or equal to 0. In the case in which the weight as an integral less than 0 we have no existence between the two eigenvalues, and the existence outside the integral of the eigenvalues. And when A is sign changing and we are in the degenerate case, we have a solution for every lambda different from 0. In the case of non-coercive case, we have non-existence. In the degenerate case, we have existence only between the two first eigenvalues if A is indefinite and the integral of A is less than 0. And in the classical case, for instance, when A is equal to 1, non-existent for lambda greater than 0, and the existence of a positive solution for lambda less than 0. Okay. I want to prove the non-existence of a non-trivial solution for the problem, for the coercive problem. I consider this general problem in which, in this problem, we have that if A is sign changing, then for every lambda between the two principal eigenvalues, the problem has no non-trivial solution. Not only the positive one, but there is no, the only solution is the trivial one. The proof, in the case, in the degenerate case, I already did the proof. Then we assume that the integral wave is different from 0, for instance, less than 0. Then the principal interval, the interval of between the two principal eigenvalues is 0, lambda 1 plus, with the lambda 1 plus, which is strictly positive. Suppose that by contradiction that U is a non-trivial solution, we multiply the equation and we integrate, and we have this equation. Of course, if this term is greater than 0, then we have only that this is, we have that U should be equal to 0. If not, we have that the integral ax u squared is greater than 0, then we can use the characterization, the variational characterization of the first positive eigenvalues, and we have that the equation is equal to 0, and here, sorry, because do you see all the
slide? Yes, we can see. Yes, we can see.
Okay. Then for the variational characterization of the first eigenvalue, we have that this that should be equal to 0 is greater than 1 minus lambda over lambda 1 plus times the L2 norm of the gradient plus the integral of u p plus 1, that should be greater than 0 if u is a non-trivial solution, and this is a contradiction. So we have no solution, no non-trivial solution in the case when lambda is between the two first eigenvalues. For the existence, the coercive problem has a positive solution, so if and only if lambda is outside the range between the two first eigenvalues. In particular, if the integral of A is equal to 0, we have that for every lambda different from 0, the problem has a positive solution. I give only an idea of the proof of this. Of course, the solution, solution are critical points of the functional associated to the problem. The function is defined on the Sobolev space H1, And in general, this function is not well defined on H1 because of this term. This term could be not well defined if U is only in H1, certainly for high dimensions. But every solution, we have an a priori estimate for the positive solution. All the positive solutions satisfy these estimates. U must be less than this constant, which depends on lambda. So that we can replace the functional with a sort of truncated functional. So we can use the following functional instead of phi lambda. And this functional behaves as phi lambda when U is, let's say, small, and when U is large, the nonlinearity behaves as U square. So is well defined on H1, and then all the critical points of phi tilde are the same of phi lambda of phi, so that we can use this new functional to find the solution. And in fact, the function is coercive, so that the infimum is greater than minus infinity, and with some estimate we can prove also that the infimum is strictly negative, so that the infimum, and okay, with some compactness we know that the minimum is achieved, and is achieved by a non-trivial solution. Okay, now we go back to the existence for the non-coercive case. Assume that A is a sign changing function, and that P is subcritical. If lambda is between the two first eigenvalues, then the problem has a positive solution. Okay, the proof. Suppose that the integral way is less than 0, so that the interval between the two eigenvalues is 0 lambda 1 plus. Even in this case, the solutions are critical points of this functional, the function of phi of psi lambda. And this function is well defined thanks to this restriction. Here we don't have an a priori estimate as before. What we do even is not so trivial to prove that this problem has a Montempa structure. Anyway, if lambda is between the first two eigenvalues, the function has the geometry. 0 is a local minimum, and we have also and the infimum of the function is man-infinitive. So we are in the geometry of the Ambrosetti-Rabinowitz-Montempa, classical Montempa theorem. The compactness is clear. We can find a critical point of this functional. This critical point is a positive solution of the problem P plus. Okay. Now I want to discuss the non-existence in the case of non-coercive problem. The proof, I give only the idea of the proof. Suppose that lambda is greater than the first positive eigenvalue. And suppose by contradiction that U is a positive solution of the problem. If U is a positive solution, then U can be seen as a positive eigenfunction associated to the eigenvalue lambda of this problem, of the following problem. Minus Laplacian of psi equal to lambda b times psi, where b is the previous weight plus u to the power of pi minus 1 over lambda, which is not equal to a, but is greater or equal to a of x. And we can use the monotonicity of the eigenvalues. By the variational characterization of the eigenvalues, we have that lambda 1 plus, which is the first eigenvalue associated to the weight A, is strictly greater than the first eigenvalues associated to B. And since we have that the only eigenfunction, the only positive eigenfunction are the eigenfunction associated to the first eigenvalue, then we have that lambda should be equal to lambda 1 plus. So we have a contradiction because lambda 1 was greater than lambda 1 plus. Okay, only only a remark on the picture that I showed before. So let's go back to the bifurcation diagram. If you see, we have drawn a solution curve connecting the first eigenvalues. This is justified by the following theorem. For every lambda greater than 0, we have that the positive solution have can be controlled. That is, there is a constant C0 such that for lambda, if lambda is controlled by this lambda, capital lambda, it holds that the norm of U lambda is controlled by this constant C0. And this is, we can prove this using Gagliardo-Nirenberg estimates. This is for every positive solution of the equation, so that we have that from the first eigenvalue, there is a branch of positive solution which goes to the other eigenvalue. Okay. Now I want to, in the last minutes, I want to discuss a little bit what happens beyond the other eigenvalues, the higher eigenvalues. We have proved that I consider only the coercive case, the coercive problem. We have proved that for lambda greater than lambda 1 and or less than the lambda 1 minus, the problem has a positive solution. And of course, a negative solution thanks to the symmetry of the function, of the equation, sorry, not of the function, but of the equation. We have that for lambda between the first and the second eigenvalue, there are no solutions that change sign. We can prove that between the first two eigenvalues, the only solution is the positive one. And but if lambda is greater than the k or less than the k negative eigenvalue, in the case, then P as P minus, the coercive problem, as k couple of solution. Okay, this is the picture of the theorem. We have no solution at all between the first two eigenvalues, two solutions, one positive and one negative, when lambda is between the lambda 1 and lambda 2, and 2k solution, which is our k couple of solution, when lambda is greater than lambda k or less than lambda k minus. The proof is related to the Krasnodębski index. We use the variational characterization of the caped eigenvalues to prove that we have these estimates. And then we use Clark's theorem, which says that if we have a C1 functional and which is an even functional, which satisfies the Palestra condition, if we consider the set of closed symmetric subset of H with genus which is greater than K, if we define this CK as the infimum over all F which is in gamma K, and then the supremum on U of the functional, if CK is greater than -infinity and less than 0, then CK is a critical value. And this ends the proof also for the higher eigenvalues and the existence of the solution. I think I can stop here, and I thank you very much for the attention.